Hey guys, today let us discuss about horizontal motion. Mechanics is a big branch of classical physics, and mechanics is subdivided into two branches, kinematics and dynamics.
Kinematics was largely developed by Galileo Galilei in the early 1600s. We have already discussed that mechanics is subdivided into kinematics and dynamics. Kinematics describes the equations of motion of objects without reference to forces, whereas dynamics is the study of the effect of forces and other influences on the motion of objects. These two subtopics combined together form mechanics.
We will be discussing about the kinematics of horizontal motion first. So let us familiarize ourselves with the equations that governs the motion of one-dimensional and two-dimensional objects. These equations of motion are revolutionary.
Starting from Aristotle to Galileo, we thought mathematics only described the perfect motion. Celestial objects and motion of objects on Earth were unpredictable and imperfect to be calculated.
We soon figured out that the equations of motion governs the motion of all objects, whether on Earth or in space.
On Earth, we have to make approximations as a greater number of factors and variables like friction and atmosphere will affect the motion in various ways.
Kinematic equations include the variables for displacement, velocity, acceleration, and time. In kinematics, we consider that the acceleration is a constant. It could be either positive, negative, or even zero. This is because we don't consider the forces that could change acceleration over time.
Let us now familiarize ourselves with some symbols used in equations of motion. The subscript 0 and I used after v or u is used to define initial velocity. The subscript t and f after v or v is used to define final velocity. The same subscripts are applied to position as well. It can be displayed as seen here. The question on your mind right now is, what are these kinematic equations of motion? There are three fundamental kinematic equations of motion. The first equation states that the final velocity is equal to the initial velocity plus the acceleration times the time. The second equation states that the position or the displacement of an object to a point of origin is equal to the initial velocity times time plus half times acceleration times the time squared. The third equation states that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement of the position of an object to a point of origin. There are two supplementary equations that are formulated from simple definitions. The first equation is the displacement or position is equal to the initial velocity plus the final velocity divided by 2 times the time. The second equation is defined as the average velocity. It is equal to the initial velocity plus the final velocity divided by 2.
Now we know the equations of motion. Let us apply them to real examples of motion.
Let's assume that you need to travel to your office from your home. You place the foot on the gas pedal and apply a constant acceleration of 4 meters per square second in this direction. So what would be the velocity after time equals 10 seconds in your journey? And how far did you travel in that particular time equals 10 seconds? We can use the equations of motion that we discussed before to find the solutions. So the final velocity is equal to the initial velocity plus the acceleration times the time. Initially, the object or the car is at rest, so the velocity is 0. So we can obtain that the velocity is equal to 0 plus 4, which is the acceleration, times 10, which is the time, is equal to 40 meters per second. So the final velocity is 40 meters per second. When going with the displacement, we can use the equation S is equal to ut plus half at squared. So the displacement is equal to 0, where the initial velocity is 0 because it is at rest, times 10, which is the time, times half, times 4, which is the acceleration, times 10 squared, where it is the time squared, which is simplified down to 200 meters. So the displacement is 200 meters in this particular direction. Let us look at another example for better understanding. If you assume a car is traveling at an initial velocity of 40 meters per second in this direction, it would see a barrier far away from it. So it would apply brakes in it. And the acceleration is minus 10 meters per second, which means the acceleration is opposite in direction, which is a deceleration. So the question we have is, how long does it take for the car to stop after applying brakes, and how far will the car skid to come to stop after applying brakes when it sees the barrier in front of it far away? Let us use the equations of motion that we discussed before to find the solutions here as well. The car would take 4 seconds to come to a complete stop after applying brakes. This is because the final velocity of the car is 0, as it is at rest when it stops. It is equal to the initial velocity 40 in this particular direction, and we would have a negative acceleration, which is a deceleration of minus 10, and also we multiply that by the time simple t. We would obtain that the time it would take to come to complete stop after applying brakes is 4 seconds. When talking about the displacement, we can use the equation S is equal to ut plus half at squared to find the displacement. So when we apply S is equal to ut plus half at squared, we can see that the initial acceleration 40 times the time 4 plus half times minus 10, which is the negative acceleration or the deceleration, times 4 squared, because the time is being squared, so t squared is equal to 80 meters. So we obtain that the displacement it would travel or skid after applying brakes to come to a complete stop after seeing the barrier is equal to 80 meters.
So guys, you can apply equations of motion to any object. Hope you guys enjoyed today's video. Have a nice day.